All right, everyone. Hello, and welcome to my channel. This is an educational channel, and we take a look at different theories of everything, go deep into them, and explore all their ins and outs, so you can appraise them and figure out if they can help you with your paradigm shifting and your awakening to 5D consciousness, your formation of a holistic worldview. And today is our 497th video on the reciprocal system of theory from Dewey B. Larson. And in 1959, Mr. Larson proposed his two fundamental postulates about how he believed that the universe operated. And then through a process of deduction, he arrived at a theoretical universe. So this is a theoretical universe, what the universe would look like if his postulates were correct, taking his postulates and carrying out their ramifications to get to a theoretical universe. And then in many of his books, he compares his theoretical universe with the so-called actual, measured, empirical universe of the legacy scientists that they had compiled in all their scientific tables through laboratory and observatory experiments. And we're looking at one of his books that does that, called Basic Properties of Matter. It's on chemistry. Many of the basic properties of matter, Larson arrives at equations for them, such as the melting point or the compressibility. And then he plugs all the atoms, all the elements, and the many compounds into his formulas and arrives at values for these basic properties and then compares them with the scientific tables. We are in the middle of chapter 15 of this book, toward the end, which is called Electrical Storage. Now, Mr. Larson has some problems here with this chapter. If you understand the reciprocal system, then you understand that for each scientific entity, scientific quantity, such as matter, energy, force, pressure, they can all be described in units that are exclusively space or time. Basically, a fraction with space or time as the numerator and time or space as the denominator, such as motion, such as speed. Speed is, the runner is running at 10 miles per hour, 10 miles of space in 1 hour of time. Space over time. That's speed. But all scientific quantities have those units, or units such like matter. Matter is time to the third power over space to the third power. And in this case, we're talking about capacitance, electrical capacitance. And Larson arrives at the units of S for the farad. But some of his associates have proposed using the units of S to the third power over T instead. And it appears as if they are correct. And when you read this chapter with that in mind, some of Larson's, some of the things he says ring a little bit hollow. And it seems as if he's kind of contorting logic a little bit in order to fit his units which works some of the time, but not all of the time. And he has to kind of contort a little bit in order to make them work uh, to his satisfaction in every case. Now, we'll continue to go over that. Let me just say that if you want to get a more thorough rundown of the reciprocal system, me to go into the postulates in a little bit of detail and discuss some of the ramifications and just the workings of the reciprocal system, then you want to watch one of my first 474 videos on this topic, where I take about 20-25 minutes to go over how the reciprocal system operates. In this video, I'm pretty much going to assume that you have some kind of working knowledge of the reciprocal system, or that you're just an adventurer and you want to go into something that you don't really know that much about. But you probably better served in going over one of my old videos and then coming back and tuning in here. I will tell you, we'll recite Larson's two fundamental postulates, as they are very short. The first postulate, which does most of the work. The second postulate is more the conditions in which the work is being done. So Larson takes his first postulate, which is really the original stuff that comes from Larson, and then he plugs it into kind of the scientific, consensus. Most scientists would agree with the second postulate, although many of Larson's followers do not, and I don't either. But I don't even really think that that's the most important thing with the second postulate, because he's really just trying to establish some kind of consensus with the second postulate, along with some working model. And I think Larson was aware of kind of the limitations of the second postulate, but recognized that this is kind of good enough for right now. The first postulate is that the universe is composed entirely of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. Okay, so there's really 4 prongs to that first postulate. The universe is made out of motion, not matter, not energy, not force, but motion. And in particular, Larson is talking about what he calls scalar motion. Scalar motion is a motion that has a magnitude, but it has no specific direction. You can envision scalar motion using a balloon that you put dots on. If you blow up the balloon, all the dots will be moving away from each other. If you contract the balloon, all the dots will be moving toward each other, but they won't be moving in any particular direction. Every dot will be moving will be moving toward or away from every other dot. The outward motion of that balloon, Larson refers to as the progression. The inward motion, he refers to as gravitation. And those are really the 2 basic forces, or in the reciprocal system. The force of the progression basically is the source of everything in the universe, and that source is manifested by turning that outward motion of the balloon into an inward motion, gravitation, which is inherent in all matter, all manifestation. And so that's the first prong. Second prong is that motion is the relationship between space and time. Space and time having no other significance other than what they are together in motion. So no independent existence of space and time, only together in motion. And motion is basically a fraction with space or time as the numerator and time or space as the denominator. Motion, space, and time come in 3 dimensions. You can think of 3-dimensional space and 3-dimensional time, what Larson calls coordinate space and coordinate time. But then there's also 3-dimensional motion, which goes beyond those because it requires 3 dimensions of space just to define 1 dimension of motion. So those 3 dimensions of motion go beyond coordinate space and time. And I would argue also then beyond Euclidean space and time, and which kind of throws some cold water on the second postulate, which we'll get to in just a second. So space, time, and motion come in 3 dimensions. Space, time, and motion come in only discrete units. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. 1 unit of space is approximately 2 millionths of an inch. 1 unit of time is approximately 1.5 femtoseconds, or 1.5 times 10 to the minus 16 seconds. And that's a very short amount of time. And if you don't have a full unit, then you pretty much are working in the other quantity. And so you use the reciprocal like that. So if you don't have a full unit of space, if 2 particles approach each other to 1 unit of space, they can't get any closer because there is no such thing as less than 1 unit of space. So instead, they move further apart in time, not in space. There is no space. There's only 1 unit of space, so they can't get any closer, but they can get further apart in time, which is the equivalence of getting closer in space because of the reciprocal postulate between space and time. So that gives you a little bit of a clue how this works, and hopefully some of the details will be fleshed out here as we finish this chapter. I think we left off where Larson is discussing, let's see, collisions do not transform accelerated motion into steady flow. If they are elastic, as the collisions of electrons presumably are, the acceleration in the direction of the voltage gradient is simply transferred to other electrons. If the force EQ, and this is part of Larson's contortions, is he's using a lowercase q and an uppercase q to describe coulombs. One of the coulombs has S as its units, and the other has T over S as the units, which are, for Larson, uncharged and charged electrons. In Larson's world, there is an uncharged electron in its natural state that is just a rotating unit of space. But an uncharged electron can take a charge, which is not an electron. It is a rotational vibration, a kind of motion, just like everything else is a kind of motion. So a charge is a rotational vibration, and it can go onto an electron, but it also can go onto an atom or a subatomic particle. So the charge on a subatomic particle or an atom is not an electron. It is a rotational vibration. And here he's using EQ. E is the electric field intensity, I believe, and then Q is the quantity. So he says if the force EQ actually existed, as present-day electrical theory contends, it would result in accelerating the average electron. The authors quoted in this reference evidently recognize this point, but they fall back on the prevailing confidence that something will intervene to save the moving charge theory of the electric current. And that's the electron. That's the uncharged electron for Larson is the electric current. Electric current is uncharged. Static electricity is charged. So the theory of the electric current from its multiplicity of problems, there must be other forces, end quote, or quote, that take care of the discrepancy. No one wants to face the fact that a direct contradiction of this kind invalidates the moving charge theory. The truth is that this concept of an electrostatic force, EQ, lowercase q, applied to the electron mass is one of the fundamental errors introduced into electrical theory by the assumption that the electric current is a motion of electric charges. As the authors quoted above bring out in the derivation of their electric current equation, such a force would produce an accelerating rate of current flow, conflicting with the observations. In the universe of motion, the moving electrons that constitute the electric current are uncharged and massless. The mass that is involved in the current flow is not a property of the electrons, which are merely rotating units of space. It is a property of the matter of the conductor. Instead of an electrostatic force, T over S squared, applied to a mass, T to the third over S to the third, producing an acceleration, S over T squared, what actually exists is a mechanical force, voltage, T over S squared, applied to a mass per unit of time, a resistance, T squared over S to the third, producing a steady flow, an electric current, current being S over T, the electron quantity over time. And that is T over S squared times divided by resistance. Furthermore, it is observed that the conductors are electrically neutral even when a current is flowing. The explanation given for this in present-day electrical theory is that the negative charges, which are assumed to exist on the electrons, are neutralized by equivalent positive, is that the negative asterisk charges, which are assumed to exist on the electrons, are neutralized by the equivalent positive asterisk charges on the atomic nuclei. And Larson uses these asterisks because he's using the conventional terminology, negative and positive here, but the way Larson works it out, it would be the opposite. Positive would be negative and negative would be positive. But for the purposes of staying somewhat in convention, he uses the asterisk. But if the hypothetical electrostatic, and this kind of just gives you the, just shows you how difficult it is to come up with a theory of everything, a generalized theory that you can apply to every subject. You have to deal with nomenclature in every field, and you have to come up with new terminology, and sometimes that, you have to experiment with that stuff. Some names work out better than other names, and Larson did run into a lot of difficulty with just the terminology that he uses, and you can't really blame him for it. You got to call it something, but sometimes when you're dealing with the past, and maybe they called something something, and it's not in harmony with what you call with the concept that is behind what you're doing. It's difficult to fit in a non-clumsy type of nomenclature. But if the hypothetical electrostatic charges are neutralized so that no net charge exists, there is no electrostatic force to produce the movement that constitutes the current. Thus, even on the basis of electrical or conventional physical theory, there is abundant evidence to show that the moving electrons do not carry charges. The identification of the electric current phenomena with the mechanical aspects of electricity that we derive from the theory of the universe of motion now provides a complete and consistent explanation of these phenomena without recourse to the hypothesis of moving charged electrons. As noted in Chapter 13, charged electrons are subject to the same forces that apply to their uncharged counterparts, as well as to those specifically appertaining to the charges. It would therefore be theoretically possible to apply a voltage and store these charged electrons in capacitors in the same manner as the uncharged electrons. In practice, however, the storage of charged electrons is accomplished in a totally different manner. A widely used electrostatic device is the Van de Graaff generator. In this generator, charged electrons are produced and sprayed onto a moving belt of insulating material. The belt carries them to a storage unit in the form of a large, hollow metal sphere. The electrons pass from the belt into the sphere, gradually building up a potential that may reach as high as several million volts. In our examination of electric current phenomena in the preceding chapters, we found that the electrons which constitute the current move from the regions of higher voltage or greater concentration or higher speed of the electrons to regions of lower voltage. In the Van de Graaff generator, electrons of very low electrostatic potential on the belt pass into a container in which the potential may be in the million volt range. Obviously, we are dealing with two different things, both having the dimensions of force and both customarily measured in volts, but physically unlike in some important aspects. It should now be evident why the term potential was not used in the preceding pages in connection with the capacitor storage or other electric current phenomena. The property of the electric current that we are calling voltage is the mechanical force of the current, a force that acts in the same manner as the force responsible for the pressure exerted by a gas. Electrostatic potential, on the other hand, is the radial force of the charges, which decreases rapidly with the distance. The potential of a charged electron in volts is very large compared to the contribution of the translational motion of that electron to the voltage. It follows that even where the potential is in the million volt range, the electron concentration in the storage sphere and the corresponding voltage may be low. In that event, the small buildup of the voltage in the electrode at the end of the belt is enough to push the charged electrons into the storage sphere, regardless of the high electrostatic potential. Many present-day investigators realize that they cannot account for electric currents by means of electrostatic forces alone. Duffin, for instance, tells us that, quote, in order to produce a steady current, there must be, for at least part of the circuit, non-electrostatic forces acting on the carriers of charge, end quote. His recognition that these forces act on the carriers of charge, the electrons, rather than on the charges, is particularly significant, as this means that neither the forces nor the objects on which they act are electrostatic. Duffin identifies the non-electrostatic forces as being derived, quote, from electromagnetic induction, or non-homogeneities such as boundaries between dissimilar materials or temperature gradients, end quote. Since the electric currents available to both the investigators and the general public are produced either by electromagnetic induction or by processes of the second non-electrostatic category mentioned by Duffin, batteries, etc. The non-electrostatic forces that admittedly must exist are adequate to account for the current phenomena as a whole, and there is no need to introduce the hypothetical electrostatic charge and force. We have already seen that the charge does not enter into the mathematics of the current flow and storage processes. Now we find that it has no place in the qualitative explanation of current flow either. Addition of these further items of physical and mathematical evidence to those discussed earlier now provides conclusive proof that the mathematical structure of theory dealing with the storage of electric current is not a representation of physical reality. This is not an isolated case. As pointed out in Chapter 13, the conditions under which scientific investigation is conducted have had the effect of directing the investigation into mathematical channels, and the results that have been attained are almost entirely mathematical. As expressed by Richard Feynman, quote, "Every one of our laws is a purely mathematical statement in rather complex and abstruse mathematics," end quote. The development of this mathematical structure of theory is an outstanding achievement, and it has had very important, even spectacular, practical results. However, these successes have fostered a tendency to forget that mathematics is not physics. It is a useful, perhaps indispensable tool for the physicist, but physical phenomena are subject to a multitude of limitations that do not apply to the mathematics that are utilized to represent these phenomena, and consequently are not recognized unless they are identified physically. The mathematical representation of space, for example, can be curved or otherwise modified, but this does not in any way assure us that physical space can be so modified. That question can be settled only by means of a purely physical investigation, such as the one reported in this work, which finds that such modification of extension space is impossible. And that is the end of this chapter on electrical storage. Chapter 16, the next one, is called Induction of Charges. And we will begin that chapter starting tomorrow. Now, I just wanted to make a quick point here, which I make in many videos, but we're not really studying chemistry, charges, and magnetism, and all of this stuff for its own sake. I mean, maybe some of you are. Maybe some of you want to invent new devices that create free energy or something. But the reason why we want to study Larson on chemistry is because Larson's theory is a general theory. It's a system of theory. And so you can plug it into any subject. So we're just trying to get a feel for how he plugs it into chemistry. And then we want to, take a look at how he plugs it into economics. See how he plugs it into physics. See how he plugs it into astronomy. See how he plugs it into religion. See how he plugs it into dream interpretation, because he has written on all those subjects. And then, by getting that kind of broad coverage, we can get a sense of how the reciprocal system works and its potential, and how we can plug it into whatever subject we want. You know, you can plug it into underwater basket weaving, or you can plug it into nutrition. You can plug it into, you know, physiology or biology or whatever subject you're interested in. The reciprocal system will deliver, but you have to understand its basic, you know, the basic postulates, and then how to employ those postulates in a field. And so that's why we take a close look at how Larson does it. And Larson admitted that he was subject to error. He believed that his theory itself was correct, but whether he applied it correctly in every instance was another matter, and that he was subject to error, and that he was welcoming of people coming along in the future and poking holes in his application of his theory, because that would move the theory along. And that sometimes it just does take the test of time, where, you know, your interpretation of his postulates and plugging it in, if it doesn't hold up, then, you know, he wants it to be replaced. And so, you know, this is all in the spirit of Mr. Larson himself, you know, to try to, you know, figure out if he applied it correctly in certain situations. In particular, Larson's one of the weaknesses of his theory, in my opinion, is the electricity stuff in particular. So, but not coincidentally, that is also my weakest field of understanding Larson, is the electricity stuff. So, you know, we're all kind of in the dark here a little bit together, but that's the nature of dealing with, you know, esoterica. You have to be able to accept the fact that there's a big mystery, and that there's a big learning curve, but the rewards are great if you actually, you know, make progress and have epiphanies, and you know, be able to apply them into other areas. Okay, well, thank you for tuning in today, and we'll be back tomorrow for chapter 16 on induction of charges. Have a great